Hello, this is chapter 13 on nuclear magnetic resonance spectroscopy, or NMR. By far, for organic chemists, NMR is the most valuable spectroscopic technique. That's why we devote a chapter to it here in our first semester. We'll deal with a lot of the other spectroscopic techniques in the second semester. But what it does, it maps the carbon-hydrogen framework of a molecule. So with proper interpretation of an NMR spectrum, you can actually figure out what types of carbons they are in the molecule, what its framework is, how its carbon skeleton is arranged, for instance, and by inference, figuring out what kind of functional groups are attached to them. And mostly it involves the arrangement, the structure of the molecule itself. You can actually get stereochemistry information out of it too, it turns out. So how does it work? We're going to be dealing mostly with proton and carbon-13. So remember, a proton is just a single subatomic particle. That's the most common isotope of hydrogen. There's proton or protium, there's deuterium, there's tritium. So we're just dealing with protons here, those single subatomic particles, but in a molecule, they're just represented by the H's that are attached to C's. Right? So we'll just refer to them as protons in NMR spectroscopy. Turns out that certain nuclei, like the proton, like the ch13 nucleus, they have magnetic spins to them. They have sort of a magnetic dipole moment that allows them to be influenced by a strong external magnetic field. Turns out they have to have a odd mass number. Even mass number substances, their magnetic nuclear spins sort of even out within the nucleus itself. So that's why ch13 is used. Remember, carbon-12 is the most abundant nucleus of carbon. So ch13 is what we actually detect in that spectroscopy. So normal molecule, the spins of hydrogen or ch13 nuclei are randomly arranged in the presence of a strong external magnetic field. Those spins can align in either one of two directions, the parallel or anti-parallel. So the spin can align itself in the same direction as the magnetic field, right? That's parallel. Right, that one and that one, for instance. Anti-parallel is opposite. You can sort of think of it like little compass needles in the presence of the Earth's magnetic field, for instance. But the key difference here is that with a compass needle, the worst thing is for it to be in the opposite direction, right? Here, the parallel orientation is the lowest in energy. It's the best. But anti-parallel is only a little worse. Okay? All of the other arrangements are less favorable, like going sideways and so on. So parallel is best. Anti-parallel is just slightly higher in energy. So we start out with those spins that are all totally arranged like that, slight excess in the parallel direction. It turns out, though, if we apply some electromagnetic radiation of a certain frequency, it turns out for the useful frequencies for us in NMR are within the RF, the radio frequency range. So much lower in energy than infrared or visible or ultraviolet. Most of the other types of spectroscopy. This involves radio frequency. That will supply just enough energy for the lower energy spin to be promoted, to be excited up into that slightly higher energy anti-parallel orientation. And if I have a stronger applied field, so if I have my sample in a stronger magnet, for instance, it requires a larger amount of energy to excite those nuclei into the slightly less favorable spin direction. So there's a radio frequency, there's a electromagnetic radiation absorbance that can happen. Just like in infrared, the vibrating bonds can absorb energy. Just like in regular visible spectroscopy, a colored substance absorbs certain colors of light. Well, certain nuclei will absorb specific frequencies of radio frequency energy in order to flip those spins from one orientation into the other. So, and like we talked about, if we have it in a stronger magnetic field, we need a higher energy radio frequency to flip those spins.